and that also people can see my mouse.
Yes, everything is fine.
All right. Hi, everyone. I'm Daan Mulder from the Research Institute AMOL in Amsterdam. I'm a PhD student with Daan Mulder. I want to say big thanks to the organizers. I've already seen a lot of very interesting talks, and I'm also very grateful to be speaking here. Together with Tom Aldridge from Imperial College, we have written a manuscript about information processing in finite time, and I want to present some highlights from that work here today. Given that we are gathered with stochastic thermodynamics enthusiasts, and also due to this time constraint, I'll immediately jump to describing the setup. The system we will look at consists of 2 bits, and our goal will be to correlate these bits. And one of the 2 bits is the data, which will not change, but rather we want to change our memory so that it aligns with the data. And we call this copying, since the state of the data is copied onto the state of the memory. And I'll first look at the infinitely slow, the quasi-static case, and then I'll introduce the finite time effects. And we will see that these finite time effects have a very surprising consequences for the optimal initial distribution, initial setting of the memory, which I'll explain shortly. So each of these bits is modeled as a bimodal potential energy landscape, and initially the bits are uncoupled. And that means that the probability of each of these 4 options is 25%, so the data can be 0, 1, and the memory can be 0, 1, and all these options are equally likely. And we will apply now a protocol to the memory, which depends on the state of the data. So we align the memory with the data. One can think of this as an interaction energy working on the memory. So the probabilities now flow from 0 to 1, or from 1 to 0, depending on the value of the data. So this process is very similar to a bit reset, but rather now the value of the final state depends on the value of the data. So after this step, the interaction stops. After the bits and the memory and the data are correlated, the interaction stops, and the energy levels are set to their initial values. So the combined system is now out of equilibrium. All 4 combinations basically have the same energy level, but they don't no longer have the same probability. The correct states have a probability of S, where S is the accuracy, and the incorrect states have a probability of 1 minus S. And the required work for this operation is actually given by the non-equilibrium free energy stored in this configuration, so the average work averaged over both states of the data. And in fact, it can be expressed as a mutual information between the data and the memory. So the cost is actually due to a reduction in the entropy of the combined system. So now I want to generalize this setup, and I want to take a look at introducing a biased initial distribution for the memory, as well as data-dependent values of the accuracy, so that each state of the data can be copied with a different accuracy. So, for example, the accuracy at which we copy state 1 might be higher than the accuracy for which we copy state 0. And here we show a contour plot for the mutual information as a function of both these accuracies. And of course, if we decrease one of the accuracies, we have to increase the other to maintain the same mutual information. And now it should be noted that after a copy operation with unequal accuracies, the final state of the memory will no longer be symmetric. The probability that the memory is in state 1 on average after the copy operation is not a half, but rather these 2 probabilities added together. And this asymmetry implies that we have to modify the equation for the required average work for this copy operation because there is free energy stored in the marginal distribution of the memory after the copy operation. And this work can be expressed as a Kullback-Leibler divergence between the initial distribution of the memory and the final distribution of the memory. And this implies that this Kullback-Leibler divergence is zero if these two are the same. Oh no, it doesn't show up the way I wanted. Oops. Oh yeah, now it does. Yeah, sorry. So the Kullback-Leibler divergence is zero if the initial distribution of the memory is the same as the average final distribution. So for example, if we copy state 1 with a higher accuracy, we also need to bias the memory towards one if we keep the mutual information the same so that the Kullback-Leibler divergence is zero. Yes. So indeed the costs are minimal if the initial distribution of the memory matches its average final state. So how does this picture change if we add the finite time costs? In order to do so, we modeled the memory as a two-state device with switching rates, and we impose that the switching rates have the following, that basically the relaxation rate of the system is constant, that the sum of these rates together is always equal to some constant. And the system is governed by this simple master equation. And the energy level determines what the ratio between these two rates is. And now using a Lagrangian approach from these, which is shown in these papers, we can actually determine what, if we want to copy within a certain finite time window, what is the optimal trajectory to change the energy level to reach a certain desired final distribution. And we can also calculate the corresponding minimal finite time cost. And these in general look, qualitatively, they look like this. So in the limit of long copy times, they approach the quasi-static cost and they decay as 1 over tau. But for very short copy times, the costs diverge because there is this finite relaxation rate of the system. And the larger the difference between the initial and the final state, the larger the quasi-static cost, and also the larger this minimally required copy time. So now I want to focus on the most surprising result we got. So as I was saying earlier, given that we want to copy the data with some mutual information, there are multiple options. We can either copy both states of the data with the same accuracy, or we can increase the accuracy for state 1, but lower the accuracy for state 0, and vice versa. Now, what choice minimizes the total work, including the finite time cost? Well, we see that there is a symmetry breaking a transition as a function of the copy speed tau. So here we plot the minimal work using this optimal protocol I just highlighted, and optimized along this contour of some given mutual information. So on the x-axis, we plot the initial probability that the memory is in state 1, so whether it's biased towards 1 or rather towards state 0. For long copy times, the optimal initial distribution is indeed symmetric. However, for short copy times, there is a broken symmetry, and the optimal protocol basically increases the accuracy of one of the states and then also biases the memory towards that state.
Just a reminder that we have entered the question in time.
Yeah, well, this is so to summarize, we studied correlations in finite time. In the high speed limit, it turns out we have this symmetry breaking transition. And we hope that this result can help to design energy efficient, high-speed computing devices. So thank you all for